Lesson 1.4 is finding limits by analytic methods. Okay, we looked at limit properties. We've looked at a little bit of graphs. We're going to start looking at some other methods of how we can find limits. Okay, there are multiple different options, and that's one of the things when you run across a limit on an AP exam is being able to look at it and kind of process through, okay, what are my options here? What can I do? How do I solve this limit? Especially when you don't usually plan to have a calculator when they're asking you to solve limits. You need to be able to come up with other methods here. So methods to analyze limits. Direct substitution. We kind of got into that a little bit yesterday, that if it is a continuous function and the graph, that means the graph will always exist from the left and the right the same, then we could just use direct substitution, put something in. Basic limit theorems. That comes to some of our properties and other theorems. We're going to talk about factoring and canceling, and then going back to direct substitution. That's a common one. Conjugate method, rationalizing the denominator and then substituting in. Number 5 is there's a couple of special limits that are just helpful to essentially have memorized. And I think those come up, is it in this lesson or another lesson that we specifically look at those? And it might be another lesson. I don't know. Somewhere we talk about a couple times throughout the year. But special trig limits, the fact that when you have the function sine x over x, and the limit as x approaches 0, it's always going to be 1, and the limit as x approaches 0 of 1 minus cosine x over x is always 0. Knowing those, being familiar with those, being able to identify, especially that first one, sine x over x, is definitely helpful. And then something that is pronounced L'Hopital's rule is how it's usually pronounced. Okay, there's 2 different spellings. This is the one that doesn't look like L'Hopital. That is something we'll learn when we talk about derivatives. So that's not until Unit 3, but that's another way to do limits, which you'll love once you get the hang of it. It's kind of sad we don't introduce it now, but you don't know how to do derivatives yet, so we can't introduce it. Okay, substitution theorem. If f is a polynomial function or rational function, then the limit of x of c of f of x equals f of c, provided f is a rational function, the value of the denominator does not equal 0. Okay, this is essentially direct substitution. If you have a basic graph where it's just going to be a continuous graph, there's not going to be any holes or asymptotes or anything like that, you can just essentially plug the value in. Okay, so you'll see what it says, and that's essentially what your substitution theorem is. Note, always try direct substitution first. If you get 0 over 0 or infinity over infinity, the goal will be to simplify the expression using algebraic techniques and then try again. Part of that is where L'Hopital's rule comes in, but part of that is also where factoring comes in. So, example 1, find the limits using direct substitution. So, if you think about 3x squared minus 5x plus 4, what is that graph?
Parabola.
It's a parabola, yes? It's an x squared graph. That's my highest power. It's just a plain old parabola. You know a parabola is just going to be one continuous curve, right? Mm-hmm. So that means we can just plug this 2 in and get our answer. Because the limit from the left, the limit from the right is going to be whatever that 2 value is. So 3 times 2 squared minus 5 times 2 plus 4. What are you getting? Okay. 12 minus 10 plus 4 is 6. Okay, B. As x approaches 2, x cubed plus 1 over x plus 1. What?
Factor?
If you know how to factor it, which... Well, and x cubed plus 1 does factor, and we'll review that at some point, definitely coming up. But here's the deal. If you can go ahead and plug the 2 in, and you don't run into a problem like 0 in the denominator or 0 over 0, just do that. Okay? We could factor this one, and we could cancel out the factor of x plus 1. We'd get the same answer, but just as easy to just plug them in as is, if you can. So 2 cubed plus 1 over 2 plus 1. What are we getting?
3.
Yep. 9 divided by 3 is 3. Okay, C. The limit as x approaches e of natural log of x over 3x. Do you remember? E is a number, yes. It's at 2.718, so on and so forth number. It's an irrational number just like pi. It's a big, long, infinite going number.
It cancels with natural log, doesn't it?
We'll get there here in a moment. Okay, so let's plug e in. When we plug in e, it's natural log of e divided by 3e. What's the rule you're remembering, Doug?
The subscript of natural log of e.
So if the base of the log matches the inside of the log, right? So natural log is base e, and then the main part in this base is e. What does that equal? No?
3.
No? What's the numerator equal? If this is, it's going to be natural log base e of e. Officially, you look at what would be the exponent.
1.
1. So you're going to have 1 in the numerator over
3e.
3e. So 1 over 3e. Okay. Officially, I think you're just supposed to know natural log, or logs when the base and the insides match, it just equals 1. But the bigger rule there is look for the exponent. If there's it equals whatever the exponent is. Okay, D. Limit as x approaches 4 of this cube root of x plus 4, so we can plug it in. What are we getting? Cube root of 8, which is 2. My brain wasn't quite caught up, and I was thinking 2? Really? Don't ask. I think my brain was doing cube root of 16 instead of 8. Okay, E. The limit as theta approaches pi over 6 of sine of 2 theta. So that means it's going to become sine of 2 times pi over 6, which is 2 pi over 6, or it's also what? Pi over 3. Now, the challenge here, what you've got to be able to do is not pull out your unit circle, not pull out your chart, not glance over at the unit circle, although that only helps you so much up there because that one's kind of blank right now, but being able to do that in your head.
It's either 1/2 or square root of 3 over 2.
Valid answer.
I don't even know. Oh, wait.
Here's my chart, right?
It's 1/2. Yeah.
If you remember that right there, because what goes in this first box? And that means the one I don't have filled out is 1/2. That means these other two are, while we're here, what are these two? Those are things we need to just be able to figure out. Now, were some of you doing triangles maybe? That will get us there, right? It's whatever you need to do. Okay? So what is the sign of pi over 3? Yeah, I'm not going to be able to underline it. And again, notice I'm doing this stuff without calculator, right?
Yeah.
This is all stuff that practice without calculator now, right? Wean yourself off the calculator on this type of stuff. Okay, what about F? Okay. Log base 3 of 5 plus 4, which is 9. I would say you can go farther. Without a calculator.
Is this where you could take the 9 and put it in the front? Or is that not what
No.
I'm...
No, that would be an exponent you could put out front.
Oh, it's a 2 log 3 of 3.
Back up a step there.
3 squared equals 9.
Okay, pause right there. Let's do log base 3 of what do we know about 9?
It's 3 squared.
It's 3 squared.
So it's 2.
So that exponent rule says if the base of the log and the inside base of the log match, it's equal to the exponent, which is 2. That rings a bell, right? That's the natural log property. That's the property we just used on the natural log, yes?
That's-
Which is why, Doug, when you said 2 log base 3 of 3, I'm like, back up. Although I guess you would have had 2 and then log base 3 of 3 if you recognize that as 1.
Right.
You
that's
would
what-
get there.
that's
Okay.
what I was doing.
I tend to go this route right here, but I see what you're saying. My brain forgot that. Because I go this route, I forgot you can go that route. Sorry. Okay. We like that type, right?
Yep.
Now, if only they were all so easy like that. If only you didn't get zeros in the denominator, 0 over 0, infinity over infinity, or things like that. Life would be grand, right?
Mhm.
Okay, what's the next up? What is the process for finding discontinuities of a rational function from pre-calculus? Okay, what do they mean by discontinuities?
Holes or asymptotes?
Right? Your vertical asymptotes and your holes. How do we go about finding those? And this is without the calculator again. How do we go about finding them, short of just graphing them and looking at the
I
calculator?
can see that sheet of notes in that chapter.
I can't.
I just don't remember. I remember the work part.
Remember what we had to start off doing before we got to that piece of paper? If I'm thinking the same piece of paper. Because are you talking about the paper that tells us when holes occur versus when vertical asymptotes occur? Or are you thinking about something? I don't know. That might have actually been Algebra 2 that we had that paper.
We had 3 examples, and maybe I may be thinking of Algebra 2 too. There's like 3 examples of it where we had to determine whether it's a whole or not.
Do we remember in like looking at an equation when holes or vertical asymptotes occur?
Remember x 0
Not when x equals 0.
and y equals 0.
No. When the
Denominator has
denominator equals 0?
Mhm.
Because discontinuities happen when a function can't exist. A function can't exist when the denominator of a fraction equals 0.
It said the denominator equal to 0.
Okay. So saying the denominator equal to 0 was part of it, but we did that, before we really did that, we had to take both numerator and denominator and factor them
Yes.
so we could look at those pieces. So as we talk about what the process for finding the discontinuity is, we're going to start off by factoring. You're going to factor the numerator denominator and you're going to simplify those. So I'm going to make that step 1. And I don't have this zoomed in today because I don't have enough slides, but I may shortcut what I write here. Factor numerator and denominator. Then simplify. Okay. Once you get it factored, you have to be able to do discontinuities. We usually talked about them. We talked about them as removable or not removable discontinuities, right?
Mhm.
Which were the holes or the vertical asymptotes. Do you remember when either of those occur?
where I have factor cancel.
Okay, which one occurs when a factor cancels?
Holes.
Holes, right? So a removable discontinuity, or these notes also called a point discontinuity. So removable or point discontinuity occurs when the factors cancel and you set that factor equal to 0, right? So I'm going to put both words up here. Removable or point discontinuity occurs when factors cancel. Okay, and I guess I will put, and that's when you set the factor, so x minus a equal to 0. Obviously, in my notes I have that in 2 lines, but I can't really think about that write like that on the bin queue. Okay, that's a hole basically. Yes, I didn't write it there, but that's a hole. What about a vertical asymptote? Holes happen when that factor in the denominator cancels with something in the numerator.
Is it whenever the denominator equals 0?
When the denominator equals 0 and that factor does not cancel. Okay, so it's basically any other time the denominator can equal 0, nothing cancels. So that's a non-removable discontinuity. Occurs when the factors don't cancel the denominator and when x minus a equals 0.
Unremovable. What's that word?
Discontinuity.
Um,
I don't know.
infinite, I think is what they use. Because we've had point, infinite, and jump. But jump is not what we need here. So non-removable. Infinite is another word you might see. Okay. I'm just going to say occurs when factors don't cancel the denominator. And of course, that is when x minus a equals 0, because you take that factor, whichever factor we're talking about, and set equal to 0. Okay, so get what you need there. So this is where it comes into plugging things in. We're going to run into problems here. What happens if we plug things in here? Did you try plugging anything in?
Well, you get 0.
You get 0 as a numerator.
You get 0 over 0, yes? That's a problem. You can't leave an answer as 0 over 0. It doesn't necessarily equal 0. It doesn't necessarily equal do not exist or anything like that. Okay, it's what is called in calculus an indeterminate form. Okay, because it's an indeterminate form, you need to find a different technique to use. Okay, for today, factoring and canceling is usually a good technique. If something doesn't factor or nothing cancels, eventually, L'Hopital's rule is a good one for this too. We don't know that yet, but that's a good one for this too. So I'm just going to say that this is and then we're going to go work this, but indeterminate form. Try another technique. Okay, so our other technique right now is, let's see what happens if we factor this. Now, I want to forget what I'm doing. So I'm still going to write my limit out front. That's a good habit to be in, is always trying to remember, okay, let's keep writing that limit out front. X squared plus x minus 6. Does it factor?
Yes. X plus 6 minus 6.
Agreed? X squared is x times x, multiplying to be negative 6, adding to be 1. We're calculus, so that's coming back to us pretty easily at this point. X squared minus 6x plus 8.
X minus 4x minus 2.
Multiplying to be 8, adding to be negative 6. Minus 4 minus 2. Oh, hey, what just happened to happen?
We have a whole.
Okay, I don't care about that whole though.
Oh,
I know that the x minus 2's can
cancel.
cancel.
Does it have to do anything about the whole?
No.
Oh. So
We're trying to find the limit right here. A limit can still exist at a hole.
right. I was just
Hold on.
confused.
Hold on. So at this point, what we have is the limit as x approaches 2 of x plus 3 over x minus 4. Now what happens when I plug the 2 in?
Yeah. 5 over -2.
And there's your answer then. Okay. The idea on this graph is if you were to draw a graph out, the graph would be continuous at that around that point. It just doesn't exist at that point. But a limit, as long as the limit from the left and the limit from the right match, they meet in the same spot, it doesn't matter if this point exists. Okay? The fact that there's a hole there, that's perfectly fine. It's just the limit from the left match the limit from the right. Okay? Okay. Next set. Graphically looking at this function, we see that just because it is undefined at a specific x value does not mean we can't find the limit. Remember, and we didn't really talk about the Hoover Dam construction example the other day, but we're going to use the graph of this function to determine the value of each limit below. Basically, that Hoover Dam construction, like they had everything, it was like an arch shape or something, they had everything built but one piece, and they're trying to figure out the height of that piece or something along those lines. And again, the limit is there, right? If they're going to meet the limit from the left, limit from the right, you have enough information to know that. So use the graph to determine the value of each limit below. So yes, we could do these more along the way of, plugging in and stuff, but we're going to talk here about the graph. So the limit as x approaches 2 of x squared plus x minus 6 over x squared minus 6x plus 8. What do you see?
The exact same equation we just saw.
Okay, exact same equation we just saw. What does this mean on the graph?
As you approach 2, there's a hole in it.
Yeah, as we approach 2, we're approaching that hole, but does the graph connect on either side of that hole? Yes. So what is that limit? The y value,
-2.5.
which happens to be -5/2 or -2.5. I know that not by looking at the graph. I know that because that's the last problem we did, isn't it?
Mhm.
Okay. What about same graph? Limit as x approaches 4. What's that plus sign mean?
From the right.
From the right.
Infinity?
Yeah.
Agree?
Yeah.
Okay. What about the next one?
Negative.
Agreed.
Now, while I'm here, let me ask you, what if, same thing, okay, what if we said what's the limit as x approaches 4?
It'd be D and E
Because
because they're different.
limit from the left, limit from the right, they don't agree, do they? Okay, so in that case you can do individual limits, but the joint limit we can't do. Okay. So, and do notice it's algebraically find limits of functions at undefined values. Consider what happens when you try to evaluate this limit using direct substitution. And again, you're going to run into problems, right? Okay. If we were to are they referring to the 2 or the 4? Probably both. Because the 2, we already talked about that we are going to get 0 over 0, right? If I had to guess, when you put, what are we getting when we put 4 in? No. Trying to. Oh, you get 0 in the denominator there is what you get. That's what it is. So, because like the top one would be like, whoops. I just need to not even write there because it's not going to let me, is it? You know, things like 12 over 0. Okay, that's a problem. Now, you will kind of learn something like 12 over 0. Guess what it often turns out to be? Infinity. And we'll work with that as we go. So, okay. And the other one besides 0 over 0 is also infinity over infinity. We haven't really run into that yet, but we will. Okay. Remember, when you get the indeterminate form of 0 over 0 over infinity, your goal is to algebraically manipulate the expression in an effort to remove the point of discontinuity. Then try direct substitution again. Let's explore a few techniques. So, notice, same equation, yes? Did you catch that? Recall in our example, there is a vertical asymptote at x equals 4. Flip back to the previous page if you don't believe me. How can we determine the behavior of a function at this value of x? And so you'll notice here in the first example, this is as x approaches 4 from the right, yes? We looked at charts the other day. It's been a couple of days ago, a little bit, right? Where if we were approaching something and trying to get closer, I don't know how much we were even talking about limits yet, but if we were trying to figure out what happens at 4, we'd maybe look at 4.1, 4.01, 4.001, things like that, right? We'd look at those really close numbers. And so that's what it's talking about right here is as x approaches 4 from the right, pick a value to the right of 4, and then analyze that simplified function. Now, the simplified function, what was our factored form? Where do I'm going to write it here. It was x
Plus 3 over x minus 4.
x plus 3 over x minus 4. There we go. Thank you. Okay, so now, why are we saying put it into that one? Well, that one's just going to be a whole lot easier to work with. So, if we pick a number to the left of 4, what number to the left of 4 do you want to use? Okay, if we use something like 4.1. So, I'm going to say 4.1 plus 3 over 4.1 minus 4, yes? So 4.1, 4.1. Okay, do some math with me. 4.1 plus 3 is 7.1. 4.1 minus 4? 0.1, 0.1. What happens as you divide something like 7.1 by 0.1?
You get 71.
What? Actually,
Oh, okay, so you're actually doing the dividing, but okay. So the idea is it moves the decimal over is what Doug's going with, right? And you get, but 7.1, you get a bigger number, right?
Yeah.
That number is getting, really 71 in terms of this problem is pretty big, isn't it?
Mm-hmm.
What happens if I make this number even smaller? Like there we use 4.1.
It's even bigger.
What happens if I say, what about 4.001 instead?
That beats 7,100.
Sure.
Yeah.
You'd move it 3 decimal places. So now you're at, it was 71, now it's 7,100. And what did we do? We got 4.001 is even closer to 4.1, isn't it?
Mm-hmm.
So where's my graph headed?
Infinity.
It's headed to positive infinity here. Okay. Because we got positive over a positive, yes. Positive divided by a positive is a positive. And if we were to have 7 point, what would it be? 001 divided by 0.001, you're getting an even bigger number. And we can keep going with this, right? But that's the idea that you need to plug into. So I guess if you really wanted to put these values, what? 7,100, this was 71, you're getting bigger and bigger and bigger. And keep in mind, at 4.001, we're technically not even really that close to 4.1. There's a lot more decimal places we could put in there if you want to get technical. Now, what happens as we approach from the left? And again, we're going to use that simplified version, right? So we're going to use the limit as x approaches 4 from the left of x plus 3 over x minus 4. We're not redoing the work. We're just using the same work we had. What do you want to plug in?
3.9.
Okay, yep. So if we're going to say 3.9 plus 4, nope. 3.9 plus 3 over 3.9 minus 4. Is that better? Now, think about what's going to change here. 3.9 plus 3, 6.9. 3.9 minus 4,
-0.1.
negative 0.1. Well, now notice you have a positive divided by a negative.
This is negative.
And so this is going to end up at negative. I want to say negative big number. Does that make sense if I say negative big? You know, it's negative 69, which it's a really big negative number. How's that? Okay. And for reference sake, what if instead we said 3.999? Are you seeing this? Okay. Wait, not quite there. Because we'd have 6.999 divided by negative 0.001, which, so now you're at negative 6,999. That jumped quite a bit, didn't it? Now it's even bigger negative number. So where are we headed here?
-50.
Negative 50.
By the way, I was wrong on the first one.
What first one?
57,001. That's 71.
Say what now?
It would be 7,001.
That's 7,100.
Oh, valid point. Yeah. I didn't catch it. I just went with it. No, valid point. I caught Hannah's mistake here. When she said 6,900, I said, no, it's going to be 6,999, but yeah, okay. We want to make this so I don't have a wrong screen. I'm not that concerned about it, but no, valid. Okay, and notice we're not using the calculators here, yes? And that's part of the point is picking numbers that we can kind of use math logic with and not necessarily use the calculators. And, you know, there's definitely something, if it was as x approaches 4, we'd have to look at both together to figure that out. Okay. Example 2. Finding limits analytically of piecewise functions and showing your algebraic steps. So I think Doug questioned yesterday or the other day what a piecewise function is. A piecewise function is basically a bunch of little graphs all put on one. And if they're all defined as one function, they're defined as like what you see here in A and B, where g of x, well, part of it is x cubed plus 1, another part of it is x plus 1. It's got two separate pieces. They don't necessarily connect. They're, you know, on different sections of the graph. So, as you look at example A, this is a common thing to see. The limit as x approaches 1 of g of x, given g of x is this function. What do you notice about the piecewise compared to the limit? We're trying to find the limit as x approaches 1. And what do you notice on the piecewise?
There's two different inequalities for
right? And the graph breaks at 1. When x is greater than 1, it's one thing. When x is less than 1, it's a different thing, yes?
Mm-hmm.
Which that means that makes it easier to do our left and our right. And that's what we're going to look here. So let's start with the limit as x approaches 1 from the right of g of x. That'd be your notation of how you write the limit as x approaches 1 from the right of g of x. What am I going to plug into to get that?
You're gonna plug the 1 into both equations.
Oh, wait, I'm just doing from the right now.
From the right. So you're gonna be from the top one.
We're going to use the x cubed plus 1 because when x approaches 1 from the right, we want to use where the graph, where it says x is greater than 1. Am I making sense? So we're going to plug this into the top one, which means it's going to be 1 cubed plus 1. Good math. Now, check the other side. What's the limit look like as x approaches 1 from the left of g of x? Well, what are we plugging into now?
The bottom equation.
The bottom equation, because when we're approaching 1 from the left, we want numbers that are smaller than 1. So we're using x less than 1. That piece of the function is just x plus 1, or in other words, 1 plus 1, which is 2. Now, our job was not to find the left and the right. Our job was to find the limit as x approaches 1. What can we say here?
Limit as x approaches 1, g of x equals 2.
And how do we know that?
Because they were the same going to the left and the right.
Yeah. The limit from the left equals the limit from the right. And a good way to write that and show this is to say the limit as x approaches 1 from the right of g of x is equal to the limit as x approaches 1 from the left of g of x. And I can use, remember I mentioned those 3 dots? I can say therefore, I get into trouble here, I'm too low. Yep, I'm in trouble. I really thought I had room, but I don't. Okay, so I'm gonna have to move it over because I can't. So what I can say, I'll put it right here, I guess. 3 dots, therefore, the limit as x approaches 1, not left or right, just as x approaches 1, of g of x is equal to 2. That right there is good AP notation. If on an free response problem you have to answer something about, you have to state a limit there, you have to prove it. You can't just say it's 2. You have to show the limit from the left is this, the limit from the right is this, and you need to state that they're equal. Stating that they're equal says my limit equals 2. Okay? I definitely did not get that exactly positioned right. That circle is off. Okay, what about B? Limit as x approaches 2 of h of x. They give us h of x, and what do you notice by coincidence?
There's 1 for the right one.
Yeah, there's an x less than or equal to 2 and an x greater than 2. And realize it doesn't matter where the equal to is, does it?
No.
Because we just care about the left versus the right. If there's no equal to, that would be fine also. So, look at the left and the right. The limit as x approaches 2, does it matter which I do first? If I say left of h of x, what are we doing here? The top equation where x is less than or equal to 2, so 2 squared minus 4 times 2 plus 7 3.
Yes.
So I did 4 minus 8 plus 7. And now, if I do the limit as x approaches 2 from the right of h of x, what am I plugging in now? Still 2, but now it's negative of 2 squared plus 4 times 2 minus 1.
11.
Me too. Mm-hmm.
I disagree.
11 for a negative?
It's the negative x squared.
Oh,
So it's the negative of 2 squared. The negative is not on the 2.
3.
So it's not negative 2.
Nope.
Quantity squared.
Nope.
Oh, okay, that's what I did.
Because it says negative x squared, that's saying you're going to take whatever x is,
Oh.
put it in, you're going to square it, and then it's going to be a negative value. When
So it'd be
So that
4
was-
plus 8, 3.
negative 4 plus 8
Yeah.
minus 1.
How would you know if it was quantity squared?
They would have
It would have said like that,
Oh.
as opposed to
Negative x.
this is saying the negative of x times x. This is saying negative x times negative x. That's an important one. We have to know the difference of it. Gets us every time. That's been getting you since algebra, guaranteed.
No, with numbers it's better because numbers they
So what do we discover here?
it's a
Limit from the left equals limit from the right, and so therefore the limit equals 3. Yes?
Yeah.
Limit as x approaches 2 from the left of h of x equals the limit as x approaches 2 from the right of h of x. Therefore, the limit as x approaches 2 of h of x is equal to 3. Okay. So that's good solid AP notation, which is why I mention it. Okay. I try and give you tips as we go through the year about things like that. Okay. You gotta get 5 more minutes of work in. In other words, the more I get done today, the less we have to do on Monday. And that means you might get this thing. I don't know if you know what it is. Work time? I know. It doesn't happen often, but it happens on occasion. Okay. Selecting procedures for determining limits. Okay. Thoughts?
to factor time.
Well, and here's the deal. You can try, and it does say factoring. Could you try and plug the number in?
Could.
Yeah.
You could, but I'm guessing you're going to, yeah, you'd get a 0 over 0.
Yeah, so then you factor.
So then we get 0 over 0, and we'd have to go back and say, okay, does it factor? Which I'll be honest, if I see any possibility of factoring, I don't even usually plug it in. I go straight back to factoring before I even try and plug it in. That's me personally. Okay, the limit as x approaches negative 4. How about this? I'll factor the denominator, you guys factor the numerator. Fair enough?
Yes.
Well, let's get the easy one out of the way. What do you know about the denominator?
4, 5.
Plus 4 minus 5.
Okay, I agree. Plus 4 minus 5. Now, numerator. Got a catch there, right? This is one you can do guess and check on. Some of you struggled to keep up with me the other day on that. You didn't really care for my guess and check. Would this be a good place to briefly review product of AC because we've slept since then? Product of AC. That means I'm going to need a product of 2 and negative 4, which is negative 8, and a sum of 7.
2x minus 4.
Hold on. So product of negative 8, sum of 7 is going to be negative 1 and 8. I'm going to use that negative 1 and 8, and I'm going to split my middle terms. Doesn't matter. So 2x squared minus 1x plus 8x minus 4. Is this coming back to us? Maybe it already did the other day, but just in case. Split it in half. GCF of the first half, 2x squared minus x. There's going to be an x in common, leaving us with 2x minus 1. GCF of 8x minus 4 is a 4. Factoring out the 4 leaves us with 2x minus 1. So one of my factors is 2x minus 1. The other factor is x plus 4. Honestly, I would have done guess and check here. Because here's some things I can tell you real quick with guess and check. 2x squared. What does 2x squared have to break into?
2x squared.
2x and x. Now, 4. What does 4 break into?
2.
It could be
2 and
2 and 2 or
1 and 4.
1 and 4. I have a 50-50 shot. Here's where my brain says, oh wait, I already factored the denominator. What do we notice about the denominator?
You need a 4.
There could be a 4 involved. The 5 doesn't help me, but should I try the 1 and 4 maybe? That's where my brain would go with this. Is, oh, 1 and 4. Well, then I'm going to put the 1 with the 2x, the 4 over here. Let's see if it works out. That's what my brain does to avoid doing product of AC. And then,
You need a positive 4 to cancel.
okay, we need a positive 4. Does that make it work if I put plus 4 here and minus 1 there? And that's where I'll check. I'm going to have positive 8x and minus 1x for outsides and insides. 8x and minus 1x. Does that make 7x?
Yes.
It does. And what just so happened to happen?
4. Right.
X plus 4's cancel. And so now I'm doing the limit as x approaches negative 4 of 2x minus 1 over x minus 5. Well, does it work? Can we do something?
Negative 8 minus 1 over negative 4 minus 7.
Negative 8 minus 1,
Negative 9.
negative 4 minus 5.
Negative 9.
Oh, what's negative 9 divided by negative 9?
1. Positive 1.
Positive 1. Okay. So this was a good example of factoring or canceling technique. If you tried the direct substitution, you found out it didn't work, right? And so then you end up having to factor anyways. Okay. And B, we'll figure out how to factor that on Monday. We'll jump right in on Monday. Because B, we have to factor that numerator. I taught you in pre-calc, maybe even in algebra 2. I taught you in both. Do you remember it? Not necessarily. Okay, homework. You can start looking at homework. You're always welcome to start looking at homework. Won't be due till Tuesday. Okay?